Okay, we are working on the Class 26 handout, 3.9, linear approximation and the derivative. So what we're trying to do is find another way to approximate the slope at a point on a curve. You know, the tangent line slope. So it looks like we did linear approximation when we found the equation of the tangent line, right? The tangent line approximates the function f for values near a point. The equation of the tangent line to a function at a point is local linearization. We're going to use a new way to do it. It can be shown that the tangent line is the best approximation in a sense that the error is smaller than using other line. Although linear approximation is not new, the way we're doing it is new, okay? So first they want us to find a linear approximation, L of x, that's this line here, right, to f of x near x equals 1. All right, so that's our point. All right, so what I did in this case before we knew the new method of doing it is I took my b, which is -1, and I found my slope by taking 2 points, the intercept, and this point 1, 1 that it goes through, right? And I found the equation of the line. The slope turns out to be 2. So here is a 2x minus 1. So to double check I'm going to say f of 1 in this case would be 1. So it matches perfectly, right? Now it says, what is the sign of the error near 1? Well, if you just look at the error equation, usually is the, oh, he has it right there. That's okay. The error equation is usually, I can actually erase on this one. Notice that our graph is higher along the y direction than our linear approximation. So our error should be positive, okay? Now find f of 1.8. All right, f of 1.8 for the real function is 1.8 squared, which is 3.24. Then I said, well, let's find the linear approximation of 1.8. I plugged in 1.8 and I got 2.6, right? So the linear approximation, if I do fx minus lx, should be 0.64. Now it says, before doing any calculation, which do you expect to be larger? The error at 0 or the error at 1? Well, the error at 1 should be 0 because we actually found the linear approximation there. So we expect the error at 0 to be larger. So let's find that. We take the two equations. F of x at 0, right, is 0. The linear approximation at 0 is -1, right, if I plug 0 into that. So it's f of x minus a -1. So my error at 0 should be 1. Okay? Moving on. Now here's where he's showing you a new equation, right? This thing here. So if we have the function at a, the derivative at a, we can find this equation. And we also, you can't see it, but I'm going to put the error equation up there. E to the x is f of x, which is all of this stuff, right? Oh no, that's the approximation. Is the real f of x minus this thing here, which is f of a plus f prime of a, x minus a. Okay? So we're going to use this on the next screen. Okay, but again, here's our, we're finding a tangent line, pretty much, but we're just finding it a little different method. All right, it says, what is the local linearization of this near 1? Okay, so what that means is, first we have to take the function, let's write this thing back up here. Our approximation is going to be f at 1 in this case, plus f prime at 1, x minus 1. We plug in those 1s. We're going to get an equation, okay? So f of 1, this f of 1, equals e, doesn't it? All right, now if I take the derivative of this function, if f of x equals e to the x squared, we're going to do the chain rule. So f prime of x, first we do the derivative of e to the x squared is e to the x squared, and then we do the derivative of the inside of this, which is 2x, right? All right, so if we figure what this is at 1, if we put 1 in here and 1 here, it's going to be 2e. So our equation becomes f of x, the approximation, is f of 1, which is e, plus f prime of 1, 2e, times x minus 1. So it's e plus 2ex minus 2e. So it's 2ex minus e. So you see we have a slope, we have a y-intercept, don't we? All right. So it says, what is the local linearization near 1? This is the equation, isn't it? That's the local linearization near 1. That's all they asked us for in this particular problem. See, we just had to find the function, the derivative, and plug in what we're finding it near. Okay? The next one says, suppose f of x is a differentiable decreasing function for all x. So our our derivative, is dropping the whole time. Okay, so it's got something going down. In each of the following pairs, which number is larger? Give us your reason. So if f of x, here they're talking about the derivatives, right? Well, if this thing's decreasing, shouldn't f prime of 5 be larger? Because if it's decreasing, f prime of 6 would be smaller. I'm going to say, since f prime of x is decreasing over all x. Now, f double prime of 5 and 0. Now, if the f prime itself was a line, I'm not sure if the derivative would be concave down or not. But if it's concave down, we would get something. We have 5 and we have 0. I'm trying to think. I'm not sure we can tell. I'm not sure I can tell easily. This one I was having trouble with too. But if the derivative is decreasing, that means the slope of this function is always decreasing. So one example of that is a parabola, right? Large slope, smaller, 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 smaller. Okay? So, which of these would be bigger? I believe, see this number here? Because at 5 plus x, it really depends where this curve is. I got to come back to this part. Okay, I'm going to revisit that. But let me move on for a second. All right, this one took me a little while, but we got it. So we have a function right here. Okay, and it says that's the range. What's the range at theta equals 20? 25510 sine of pi 20 over 90, right? So it should be 310. I don't know how far you want to approximate that or round it off. So now I want to find the linear approximation near 20. So near 20, this thing is going to be the function at 20 plus the derivative function at 20, x minus 20, right? So let's take the derivative of this thing. So it's going to be 25510 cosine, right? Derivative of sine is cosine. And then the derivative of the inside for our chain rule which is just pi over 90 because theta is our variable, right? So I'm going to put pi over 90 up here. So here is our derivative, isn't it? F prime of this x. So what I did was, we know f of 20. This is the function at 20, right? Let's find f prime at 20. And when I plug that in, I end up with, where are we? F prime of 20 is 890.4. Just plug 20 in there, right? All right, so this is going to be 310.824 plus 890.4 x minus 20. So let's simplify. 824 plus 890.4x minus 890 times this 20, which is 17,808. And when I collect like terms, my linear approximation, right, its approximation is 890.4 x, or theta, I guess I should call it theta, shouldn't I? Theta minus 17,497.2. So there's my linear approximation, okay? Now, in the next question, I put this back up here, but it says find the range and its approximation. So let's go back to the original equation. If I find the original equation, you know, this is the range. I just plug it in there. I get 326.364. Now here's what was throwing me. I'm going to call this the approximation one. I plugged that in and I got this number, which seemed really high. So, but I double checked it. I looked at it a bunch of different ways. So E of 21 here is the function at 21 minus the approximation at 21, right? So it'll be 326.364 minus this 1201.2. And if I calculate that, I get 326.364 minus 1201.2. So my error is a negative 874.84. So really what this is showing is that that linear approximation really only holds very, very close to 1. We're talking tenths or hundredths different from 1. It does not even hold for a 1 degree difference in this problem. Okay, so this, go through this, see if you have questions. I'm going to come back to this page right here. I got to get a better explanation for you. Okay? All right, thanks, dear.